Deep beneath the surface, pipelines face constant threats. Corrosion and erosion slowly destroy the metal.
Welcome to this video on corrosion and erosion in subsea infrastructure, prepared by Dr. Qureshi from NUS. He specializes in the area of flow assurance and provides consultancy. This module focuses on the integrity management challenges posed by material degradation in subsea environments. In this first part, we will examine the fundamental corrosion mechanisms that led to the chemical degradation of pipeline steels. Corrosion is an electrochemical process where metal reacts with its environment. In subsea systems, acidic gases like carbon dioxide and hydrogen sulfide are the primary drivers of internal corrosion, which can lead to leaks, ruptures, and significant environmental threats if not properly managed. Sweet corrosion occurs when carbon dioxide dissolves in free water, forming carbonic acid. While iron carbonate scale can sometimes form a protective layer, industry models are used to predict corrosion rates based on operating conditions. The chemistry of sweet corrosion involves anodic dissolution of iron and cathodic reduction of carbonic acid. If conditions allow, iron carbonate precipitates, potentially providing a protective layer against further metal loss. Sour corrosion, driven by hydrogen sulfide, is particularly dangerous. Unlike the generalized thinning seen in sweet systems, H2S is known for causing sudden, localized, and brittle failures in high-strength steels without warning. Two primary H2S cracking mechanisms are sulfide stress cracking, where atomic hydrogen embrittles the steel, and hydrogen-induced cracking, where internal pressure builds up at laminations to form blisters. This table highlights the differences between sweet and sour corrosion, from the specific acids involved to the unique mitigation strategies required, such as material hardness control for sour service. Top-of-line corrosion, or TLC, occurs in stratified flow when water vapor condenses on the top of the pipe, absorbing corrosive acids. A significant challenge here is that liquid inhibitors injected into the flow stream often fail to reach these upper surfaces. Microbiologically influenced corrosion, or MIC, involves bacteria like sulfate-reducing bacteria that thrive in oxygen-free environments. They produce H2S directly at the metal surface, causing severe pitting that requires specialized biocides and pigging for mitigation. We now move to part 2 of our module, where we explore erosion and the complex synergistic effects it has when combined with corrosion. Sand erosion is a purely mechanical process where particles impact the pipe wall. Vulnerable areas include elbows and manifolds, where flow direction changes and particles deviate from the fluid's main path. Erosion and corrosion often work together in a destructive feedback loop. Mechanical erosion strips away protective scales and inhibitor films, exposing fresh, bare steel to acidic fluids and significantly accelerating the rate of attack. Key factors that accelerate this synergistic damage include high gas velocities that increase kinetic energy, high water content providing the medium for reactions, and elevated temperatures which drive faster reaction kinetics. Finally, managing these risks requires balancing fluid velocity. The goal is to keep flow fast enough to prevent sand deposition and liquid loading, while remaining below erosional limits to avoid accelerating the combined threat of erosion and corrosion. We are now moving into part 3, where we discuss the strategies for material selection and the various protection methods used to ensure the long-term integrity of subsea infrastructure. When selecting a material strategy, we weigh CapEx against OpEx. Carbon steel with chemical inhibitors offers a lower initial cost but higher running costs, whereas corrosion-resistant alloys require a higher upfront investment but provide long-term passive protection with minimal chemical requirements. Corrosion-resistant alloys rely on high chromium and molybdenum content to create a self-healing passive oxide layer. Duplex stainless steels provide high strength and pitting resistance, while nickel alloys like Inconel 625 are essential for extreme, sour, high-temperature service. Where do we use these alloys? Clad pipelines bond a thin CRA layer to cheaper steel to save costs. Subsea hardware, which is difficult to replace, often uses solid CRA, while chemical injection umbilicals use superduplex to withstand aggressive production chemicals. For external protection, we utilize cathodic protection, or CP. By shifting the electrochemical potential of the pipeline, we turn it into the cathode of a cell, effectively preventing oxidation and rusting from the corrosive seawater environment. Sacrificial anodes are the standard CP method. These are highly active metal blocks, often aluminum or zinc alloys, that we attach to the pipeline. They corrode preferentially, donating electrons to the steel and thereby sacrificing themselves to keep the pipeline intact. For internal chemical inhibition, we use film-forming amines. These are surfactants that adsorb onto the steel wall, creating a hydrophobic barrier that stops corrosive aqueous fluids from contacting the metal surface. However, using inhibitors presents challenges. They must properly partition into the water phase to be effective, resist being stripped away by high shear forces, and remain compatible with other production chemicals like hydrate inhibitors. In Part 4, we examine how we verify that these integrity measures are working through various monitoring and management techniques. Subsea monitoring tools are critical for verifying system integrity throughout the lifecycle of the asset, providing data that helps us confirm our corrosion models and protection strategies are performing as expected. Inline inspection tools, or intelligent pigs, traverse the pipeline to scan the walls. Magnetic flux leakage detects field changes at wall thinning, while ultrasonic testing provides accurate, absolute thickness measurements, provided the pipe environment is clean and liquid-filled. Risk-based inspection, or RBI, allows us to optimize resources. By assessing the probability and consequence of failure, we can move away from arbitrary inspection schedules and focus our efforts on the pipeline segments that pose the highest risk to the system. Managing pipeline integrity is a life cycle process. It starts at the design phase with corrosion modeling, continues through operations with active monitoring, incorporates regular inspections, and concludes with fitness for service assessments based on the gathered data. To summarize, different assets pose distinct threats. Erosion and corrosion are synergistic and destructive. Material selection is an economic balancing act, and predictive models must always be validated by real-world data. Thank you for watching this module on corrosion and erosion in subsea infrastructure. We look forward to seeing you in our next session on 1D transient thermal modeling. If you are interested in discussing consulting engagements, joint research, or professional training, please feel free to reach out via the contact information displayed on the screen. Thank you for your interest, and I look forward to connecting with you.